project.
Okay, so good evening. Welcome everyone to this special lecture today as a part of the online interactive lecture series, which are being organized by the INO project. Today we have a very popular speaker, Professor Patrick Das Gupta. I'm sure many of you have heard him many times, and he is probably one of the most popular speakers on the subject. And incidentally, I never heard him, and so it's a great opportunity for me to listen to his lecture today. He's going to speak on exotic physics from monopoles, sterile neutrinos, and all that. That is the title of his talk. I want to take a couple of minutes to formally introduce today's speaker. After receiving the National Science Talent Search Scholarship way back in 1976, Fritz Pilani to do a 5 years integrated MSc physics. In 1981, he took admission initially for a PhD program at Indian Institute of Science, Bengaluru, but left for TIFR, Tata Institute of Mumbai, and in 1982 as a research scholar in the theoretical astrophysics group of TIFR. And soon after finishing his PhD in 1988, he joined IUCAA in Pune as a postdoctoral fellow. And during 89, 90, couple of years, he had a short stint at the University of Wales, UK as a senior research fellow to learn about gravitational wave data analysis techniques, as well as at the, I hope I can pronounce it properly, it's a French name, Observatory de Paris, to have an exposure to the topic of gravitational radiation from, say, tailored binary pulsar. He joined the Department of Physics and Astrophysics, University of Delhi in 1993 and has been full professor there since 2004. So his areas of research areas include studies related to confirmation of Hawking area theorem from the observed gravitational waves from binary black holes, proposing a unified model of gamma ray bursts and fast radio bursts, modeling dark energy, Torsen and Kem Simon gravity using a dynamical four form, mechanisms to generate supermassive black holes from Bose-Einstein condensation of bosonic dark matter, as well as birogenesis from primordial black holes. Currently, he is working on gravitational waves from interacting Dyons, as well as accelerating universe. Of course, apart from all these very serious research studies that, of course, he is engaged in, apart from teaching at the University of Delhi, but he is very popular, and as that is how I think many of us got connected to him. Is also been very active in training and leading students for the International Olympiad under the aegis of Homi Bhabha Center for Science Education, TIFR. And as I said, he's also a very popular speaker across the length and breadth of this country. So we very much look forward to your excellent talk, Patrick, today. Suppose I now request Patrick to start his lecture. Patrick, can you hear me?
Sir, could you please mute Fiza Khan?
Yeah, I'll do that, but I want to get the speaker on. Just a second, I don't see his cell phone connection.
Yes, he seems got disconnected from phone.
Yeah, exactly. Okay, I think he's trying to send me something. Yeah, but
Hello,
Yes, hi.
am I audible now?
Yes, yes.
Okay, okay,
Yeah.
great. Okay,
Sorry, we
so
missed you for a while.
yeah, I think due to some reason, the whole thing got muted.
Okay.
So thank you, Dr. Satyanarayan Bisat, for giving me this opportunity to speak to many young members and also my esteemed seniors like Professor Rajshekharan. I'm glad to be giving this talk. Basically, this is some work which I am doing with my PhD student Mohammad Sartaj on Dion-Dion interaction and generation of gravitational waves. And the second theme, which is on sterile neutrinos, is a work which is being done by Priyamvada and Varun Srivastava. Priyamvada is my graduate student, and Varun Srivastava is a MSc student from ISER Kolkata. All these are work in progress. The reason I decided to give it any how is because COVID-19 is all around, and who knows whether I get a second chance. So might as well talk about it. So can you go to the next slide, please?
Yeah.
Yeah. So this next slide. Yeah, I initially wanted to name the talk as Quixotic Physics regarding monopoles and sterile neutrino, but then you might take me to be Don Quixote trying to attack windmills, thinking that they are giant enemies and will not take it seriously. But notice that the blades of the windmill, they resemble the electric field of the magnetic field out of the monopole. Similarly, here there is a smaller version which is like neutrinos. Next slide, please.
Yes.
Next slide. Yeah. So these are the blades of the windmill. Next slide.
Yes.
And the neutrinos here, the question mark, of course, represents the hypothetical sterile neutrino. Next slide, please.
Yes.
And the second theme, which is an idea that could sterile neutrinos, which themselves are, of course, hypothetical, could they be generating anti-gravity? So you might think, again, this is a very crazy idea, reminding one of the Baron Munchausen stories. Those who have read Baron Munchausen story must have read one story in which, in order to save himself and his horse from drowning, the way he pulls himself up from the pool of water is by pulling up his hair. Now, Baron Munchausen stories, of course, tell us what is not really possible in physics. I hope the sterile neutrinos generating anti-gravity is not such a Baron Munchausen-ish idea. Next slide, please.
Yes.
Yes. So everyone has seen a bar magnet, but we also know that if you split a bar magnet, it doesn't come out in terms of North Pole and South Pole. Each pieces themselves carry both the poles. And that's basically because of the fact that, am I audible?
Yeah. Very much.
It's because of the fact that the atoms, the iron atoms themselves are like tiny bar magnets because it carries a unpaired spin, and because of the charge, the spin with charge behaves like a magnetic dipole moment. But always physicists, starting from Pierre Curie, Thomson, they had been always wondering about magnetic North Pole and magnetic South Pole because they make the electrodynamics Maxwell's equations very symmetric. Next slide, please.
Yeah.
Yes. So as you can see, the middle panel doesn't have any magnetic monopoles, but the rightmost panel, when you put the magnetic monopole charge density and similarly magnetic monopole current density, the extended Maxwell's equation have a greater symmetry. And just like your del E by del T, they represent a displacement current, which tells us that when charge flows from a battery onto charging a capacitor, del E by del T increases, maintaining the continuity of charge conservation. Similarly, if you had magnetic currents, completely magnetic world, del B by del T will then be the corresponding magnetic displacement current. So the moment you introduce magnetic charges, the extended Maxwell's equations have a greater symmetry. Next slide, please.
Yeah.
And this symmetry corresponds to a rotation in the space of electric and magnetic field. It's called the electromagnetic duality symmetry. And the rotation is parameterized here by angle alpha. Next slide, please.
Yeah.
And one can ask whether such a U1 symmetry can be gauged. And the answer is, it is possible to gauge the electromagnetic duality symmetry, but it comes with a price, namely the charge parameters, they become space-time dependent. But I will skip a whole lot of these slides because at the moment, they are not part of the main topic. So please skip 3 or 4 slides.
Should I go further? I'm at...
yeah, please continue skipping.
We are at a monopole.
Here, please start.
Yeah.
So now Dirac, he rejuvenated the whole idea of the magnetic monopole by considering quantum mechanics of charge particle around magnetic monopole. So what Dirac did was he imagined a very thin solenoid, which is semi-infinite. So the end point of a infinitely thin and long semi-infinite solenoid can be considered to be a magnetic monopole, because from one end, the magnetic fields will be coming out radially outwards. And the way he took care of considering a charge interacting with such a magnetic monopole is he imposed a condition that the charge particle should not see this infinitely thin string, the so-called Dirac string. After all, it's just a hypothetical quantity. And lo and behold, when he imposed that condition, he got the famous product of the electric charge times magnetic charge quantization. Next slide, please.
Yeah.
And so this is just the fact about the quantum mechanics brings about a whole lot of surprises. Next slide, please.
Yeah.
Yeah. So one can understand the quantization from the following 2-slit experiment. So imagine that you have a thin solenoid between 2 slits, and you have electrons, or for that matter, any charge particle having the setup of a 2-slit experiment. Then the wave function corresponding to the charge going through slit number 1 would be given by this expression, where psi1 RP would have been the wave function had there been no solenoid, while the wave function corresponding to slit number 2 is given by this phase term multiplied by psi2 RP. Again, psi2 RP is the state corresponding to the electron passing through the second slit. Now, one can easily show that as long as there are no magnetic field around, such a wave function where the integral, line integral of E dot dl essentially acting like the phase, this entire thing is a solution of the Schrodinger equation. Now, the point is that if you have indeed a thin solenoid where the magnetic field is only inside the solenoid, outside there are no magnetic field at all. So therefore, this ansatz will work. This entire thing is a solution of the Schrodinger equation. But if you take one of the phase factors outside, then because of the paths being directed, so when this phase factor is taken out, you get a minus thing, and the whole thing is a loop integral, contour integral of the vector potential all around the solenoid. So although there is no magnetic field outside the solenoid, but by virtue of the Stokes theorem, the contour integral of A dot dl is same as the surface integral of curl of A dot dA, but curl of A is the magnetic field, and hence what this quantity represents is the magnetic flux, that is B dot dA integrated over the surface area enclosed by this dashed line. And indeed, since there is a solenoid present and therefore magnetic flux is non-zero, and hence if there is a solenoid, there will be a phase shift in the interference pattern, and this Aharonov-Bohm effect was indeed experimentally measured. Now you might ask, what has got this to do with the magnetic monopole? The idea is that you can use this to explain the product of electric charge and magnetic charge quantization in the following way. Imagine instead of a solenoid, you have a magnetic monopole very, very far away, and the so-called Dirac string, the line along which the vector potential is not defined, that string, if it is crossing this area, then indeed the B dot dA, if you integrate the magnetic flux around a loop, then it will be nothing but 4 pi times the magnetic charge. Because after all, by Stokes' theorem, the integral around a tiny loop is same as the integral around a surface area where there's just one hole out here. And therefore, if you have a magnetic monopole very, very far away, only the Dirac string is crossing this, this entire quantity will be 4 pi times magnetic charge, and therefore the electric charge times 4 pi magnetic charge divided by h bar c has to be integral multiple of 2 pi. Why? Because after all, the Dirac string is only a mathematical artifice. There is no solenoid there anyway, and therefore there should not be a shift in the fringe pattern. And hence, that explains that if you have a magnetic monopole, E times 4 pi magnetic charge divided by h bar c must be 2 pi n, and that gives us the famous Dirac quantization condition. Can I have the next slide, please? Right. So one gets the charge quantization. And next slide, please. This is just a repeat of the previous one. So we can go to the next slide.
Yes.
So this entire application of Aharonov-Bohm phase to magnetic monopoles and superconductors, there's an elementary exposition to this in my article in a book titled Lectures on Quantum Mechanics. Those who are interested in seeing the application of Aharonov-Bohm phase may go through this article. Next slide, please.
Yes.
Right. But now the question is that while Dirac quantization tells us that if there is a single magnetic monopole anywhere in the universe, that can explain why electric charge is quantized in steps of h bar c divided by twice magnetic charge. But the question remains, are there magnetic monopoles around? So one important astrophysics bound was discovered by Parker. He used the argument that if there are magnetic monopoles, then they will short the magnetic fields of the Milky Way galaxy, because the magnetic monopoles will be accelerated by the magnetic field lines. And as the magnetic monopoles get accelerated, their energy increase, and this energy comes at the cost of the magnetic field energy. So presence of magnetic monopoles would essentially cause decay of the magnetic field. But of course, magnetic fields are also generated by dynamo processes. That means the plasma current going around can also regenerate the magnetic field. So by balancing the decay rate of the magnetic field due to magnetic monopoles and regeneration of magnetic field through dynamo process, Eugene Parker obtained this bound that even if there are magnetic monopoles, the flux must be less than 10 to the power minus 15 per centimeter square per second per steradian. Then, of course, when grand-unified theories with the solution of 't Hooft and Polyakov, the so-called gut monopole, it was shown by Kibble that Big Bang universe would predict one monopole per horizon in the early universe. That means today one should be having a huge lot of monopoles all around. And that's a problem because Parker bound gives a stringent upper limit to the flux. And this led to Alan Guth invoking an exponential phase of expansion of the universe to dilute the monopole density. Of course, inflationary cosmology paradigm also has other virtues, namely it can explain why is it that two diametrically opposite points that the temperature of cosmic background radiation is same, although those seem to be beyond each other horizon. And similarly, the other problem of the closeness to a flat universe. Let me not go into it, but let's come to other searches. Here there's a typo. It should be MONDL. This is Professor Nobomondal. So in late 1970s, Professor Nobomondal and other members were involved in searching for magnetic monopole at the observatory in Kolar gold mines. Similarly, recently, Professor Datta's group, they have used the INO-ICAL detector to give bounds to the monopole flux, and their bound is about flux less than 7 into 10 to the power 8 into 10 to the power minus 17 per centimeter square per second per steradian. Can I go to the next slide, please?
Yes.
Yes. So after the whole lot of work on magnetic monopoles, I must mention Meghnad Saha in 1936. He gave a different way of explaining the charge quantization, the quantization of magnetic charge times electric charge being nh bar c by 2 by invoking the quantization of the angular momentum of the electromagnetic waves. It's a very interesting exercise. Those who are doing their MSc can sort of go along the argument that Meghnad Saha had presented. Soon after, the screen has got minimized, but doesn't matter. I can, yeah. Soon, in 1969, Schwinger, he gave the idea of Dion, that is monopoles that also carry electric charge, because he was interested in talking about the nuclear matter. And thereafter, the so-called BPS Dyons, Julia and Z Dyons, and Witten, Ashok Sen, the whole idea of Dyons coming out of various theories, even electroweak theory predicts Dyons, that was shown by Julia and Z. And the theoretical models indeed suggest existence of such Dyonic solution. And now here, what we would like to ask is that, well, if you have pair of massive Dyons, when they interact, they would certainly emit electromagnetic waves as well as gravitational radiation. And this is the work which I have been doing with Mohammad Sattaj, my PhD student, and we are in the process of writing it up. Incidentally, Partho Majumdar, along his student, they had worked on very high energy point charge particle moving across a monopole, but they did not discuss the generation of electromagnetic waves and gravitational waves from such interaction. They essentially showed that electromagnetic effects are very important when you have such ultra-relativistic scattering of charged particle due to a monopole. Next slide, please.
Patrick, if I can, so your screen is okay, or you said something?
Yeah, the screen is fine. Now the screen is
okay.
fine.
Okay. And also, Professor Datar wanted to just interrupt and kind of, he kept a message in the chat box just to clarify that
yes.
The ones that you quoted coming from ICAL are actually calculations of the sensitivity of ICAL detector and when it is built for the magnetic monopole. So these are actually
so this is the projected upper
sensitivity of the ICAL.
Yeah. Right. Thank you for the clarification.
Yeah. Okay. So now I went to the next slide.
Yeah. So the problem I would just allude to is that supposing you have two Dyons, one Dyon carrying charge Q1, magnetic charge G1, mass M1, and the other charge Q2, magnetic charge G2, and mass M2. Now we would include not only the electromagnetic forces, but also the gravitational forces. Next slide, please.
Yeah.
And one can trivially work out that if these two Dyonic systems are moving with non-relativistic speeds, then the equation of motion is given by this. So there's the gravitational interaction, there's the electrostatic interaction, magnetostatic interaction, but also there are Lorentz force terms coming in because the charged particle is moving in the field of magnetic monopole, and therefore you have the cross product terms also. And this is a very interesting mathematical problem. Next slide, please.
Yeah.
And one can easily prove there are three constants of motion: the total energy and the orbital angular momentum. From that, you have to subtract the contribution of the electromagnetic angular momentum, which is proportional to the unit vector that connects the magnetic monopole, which connects the two Dyons, and the square of the orbital angular momentum is also a constant. And next slide, please.
Yeah.
And one can work out that if you consider a simple case of a monopole, that means the electric charge of the particle 1 is 0, just magnetic charge is present, while the second particle has electric charge, no magnetic charge. And if the masses of the particle 1 is 29 solar mass and particle 2 is 36 solar mass, you can guess that these masses have been chosen because these were the first case of the gravitational wave that was detected, two black holes weighing 29 solar mass and 36 solar mass. And one can work out exactly the trajectory without taking the radiative back reaction due to electromagnetic waves and gravitational waves. And one can work out the exact trajectory. Next slide, please.
Yeah.
So this is a trajectory of the particle, the two black holes one carrying magnetic charge, the other carrying electric charge. And you can see the usual conical, the spiral around a cone, that's the hallmark of magnetic monopole and charge interaction. Next slide, please.
Yes.
Now one can ask after all, these particles, these dyons, they also have dipole moment as well as magnetic dipole moment, and they, as they move about, the both electric dipole as well as magnetic dipole change with time, and one can work out the kind of electromagnetic power that is emitted. And for the case I just showed, the electromagnetic power is indeed huge. It is of the order of 10 to the power 65 erg per second. Next slide, please.
Yeah.
And the electric field X component, it varies in the following manner. It rises as they come closer, the electric field increases. The Y component also has a similar behavior. Next slide, please.
Yeah.
I think next slide is the,
Yeah, this is
yeah, now let's go to the gravitational waves emitted from such a dionic pair.
Should I go to next slide?
Yeah, next slide.
Here.
Yeah, because we know that whenever any matter system moves and there is the mass quadrupole moment changes with time, here I have shown the first direct detection of gravitational waves from two massive binary black hole, one having mass 29 solar mass, the other having mass 36 solar mass. And we know, because gravitation is a universal force, any object which moves about and its mass quadrupole moment changes would lead to gravitational waves. Next slide, please.
Yeah.
So in our case, if you have two dyons going about each other, they will also release gravitational wave. Next slide, please.
Yes.
And since the gravitational waves amplitude depend upon the second time derivative of the mass quadrupole moment, while the power released depend upon square of the third derivative of the quadrupole moment, one can estimate for our problem, for the dionic problem, we show that gravitational power that is generated from such system is about 10 to the power 54 erg per second. Next slide, please. Yeah. So in other words, the effect of electromagnetic interaction as well as gravitational interaction, they lead to different gravitational waveform. Here is the plus polarization of the gravitational waveform shown. And in the next slide, the cross polarization will be exhibited. Next slide, please.
Hello?
Next slide.
Should I go to the next slide?
Yeah, next slide.
Okay. Yeah, now I can.
Yeah, thank you. Yeah, so there's the cross polarization. I think we have to skip several slides. We will straight go to the fast radio burst. Yeah, so there's a table which shows various cases of mass. Let us, previous slide, please. Previous slide. Previous slide, please. Yeah, there's the one. So okay. We have worked out for different, for different pairs of dyons and charges, we have worked out the gravitational wave power, electromagnetic power, etc. Next slide, please. But interestingly, next slide.
Yeah, went to parameters.
Yeah. Are you able to hear me?
Yes, but there's some problem about this is not very quick. Yeah. So we'll manage.
Oh, I see. Yeah. So in this slide, you see that there are two mass parameters. If you have dyons, which are planetary size, they are the masses of the order of Earth masses. Then if one of the dyons has electric charge, dimensionless electric charge, that is charge divided by square root of g times mass of the object, 10 to the minus 3, and other having magnetic charge satisfying the Dirac quantization condition, then interesting thing happens. The electromagnetic power is of the order of 10 to the 44 ergs per second, while the frequency is of the order of gigahertz. Now, why is this important? Next slide, please. There's a whole class of objects which have been recently discovered. We will skip 2 or 3 slides now.
Okay. Now,
let's skip this also.
X component of electric field.
Let's skip this.
Okay. Then gravitational wave amplitude.
Let's skip that too.
Cross polarization. Now we are here, fast radio bursts.
Yes, that's where I would like to come.
Okay. Can you see the screen?
Yes, there's the one. There's the one.
Yeah.
Yeah.
Okay.
So in recent times, one of the class of astrophysical sources have been creating a lot of flutter, namely the fast radio burst sources. And here is a sort of artist's conception of a mysterious source erupting and generating a single pulse of radio wave, and that has been detected by terrestrial telescope. Next slide, please.
Yes. I changed it. Can you see?
Yes. So the first fast radio burst was actually detected serendipitously by Lorimer and his group by surveying the pulsar archival data, and he found that there's case of a single narrow peak of radio burst whose frequency, as you can see, is in the gigahertz domain, and it started the whole field of fast radio bursts. Next slide, please.
Yeah, FRBs.
Yes. Currently, there are about 130 FRBs. Many of them have been detected in real time, and they are seen in the frequency range 400 megahertz and 2 gigahertz. This is the frequency which is very important. The moment we found the magnetic monopole and planetary size magnetic monopole and electric charge objects, when they move about, they produce such 2 gigahertz. We thought that we can ask, can we explain the fast radio burst using this interacting planetary size magnetic monopole and electric charge? And next slide, please. The currently popular models for the FRBs are either magnetas, which are pulsars having magnetic field more than 10 to the 14 Gauss. Next slide, please.
Yes.
Or the Falcke-Rezzolla model, which is about collapse of supramassive pulsars as they lose their angular momentum due to magnetic braking. Now, with my student Nidhi Saini, I worked out that if you have supramassive magnetas, which by Falcke-Rezzolla model collapse, they, under certain condition, can also explain a half a dozen or so repeating or recurring fast radio bursts. It could be that they form curved black holes embedded within magnetized plasma. Excuse me. I'll just have a sip of water.
Yeah, sure, please.
Or you could also invoke the collapse of these magnetas into strange quark matter, but that's a different topic. the question of FRBs is still open. We don't know how FRBs are generated. So this new, that is why the so-called exotic physics, the question is whether we could explain the recurring FRBs using planetary size black holes, one carrying magnetic charge, the other carrying electric charge. Next slide, please.
Yeah.
Yeah, so indeed, if in the cosmos you have planetary sized black holes, one having electric charge, the other having magnetic charge, they can give rise to the right kind of power that is seen in FRBs of the order of 10 to the power 42 to 10 to the power 45 ergs per second and gigahertz frequencies. One might ask that how likely is it to have black holes in the cosmos that are electrically charged, and similarly black holes, large black holes having magnetic charge. And now Wald, way back in 1974, had outlined a way to have charged black holes. The idea was that if you have a rotating black hole embedded in plasma, which creates magnetic field, then such black holes can become charged by effectively absorbing only one kind of charge from the cosmic ray particles. And the kind of charge, whether positive or negative charges are absorbed, will be determined by the inner product of the angular velocity with the magnetic field. So you can indeed land up with magnetic electrically charged black holes. Similarly, mathematically, of course, one has magnetically charged black hole solution, but one way to have massive astrophysical black holes with magnetic charge is that if you have stars in the early universe, that is the first kind of stars, they could have absorbed magnetic monopoles, and later on, when the first so-called population 3 stars, when they exploded, leaving a black hole as relic, those black holes can bear magnetic charge. So in other words, what one is saying is that the monopoles that were around in the early universe, the density would have been very large. They could have been absorbed by the population 3 stars, the so-called first stars of the universe, and the monopoles, the population 3 stars, when they explode in the form of gigantic supernovae, the relic black holes can carry these magnetic charges. But of course, the main problem, that's the reason these are exotic physics, we still don't know what kind of number density of such magnetically charged and electrically charged black holes are there in the universe. At the moment, there are only possibilities. To get a realistic estimate, we have to do much more work to find the abundance of such electrically and magnetically charged black holes. Next slide, please.
Yeah.
Yeah, so this is how the electric field and magnetic field vary for such planetary size black holes that interact via electromagnetic interaction. Next slide. Let's go into the sterile neutrino part, because I think I'm running out of time.
Here, the slide says summary.
Yes, so this is just a summary that the reason why the main motivation for working out the interaction between magnetically charged black hole and electrically charged black hole was to have a new model for this fast radio burst, because we showed that planetary sized black holes carrying magnetic charge and electric charge indeed can produce the fast radio burst kind of luminosities at 1 to 2 gigahertz. But of course, as I said, the abundance and the large charge to mass ratio, the details have to be worked out. Next slide, please. Now I will go to a different topic, which is more in tune with the INO, namely anti-gravity of, we are postulating what if sterile neutrinos are source of anti-gravity. So this is a Hubble deep sky picture of the contents of the universe. You can see that the basic constituents of the universe are galaxies. Next slide, please.
Yes.
And in 1929, Hubble showed by looking at the redshifts of the emission lines of matter from external galaxies that the Doppler shift, he interpreted them as Doppler shift. Today we know it's not Doppler shift, but he essentially said that the Doppler shift is proportional to the distance of the galaxy from us. Next slide, please. And that gave rise to the entire expanding universe, so-called Big Bang model. But today we know that in reality, the galaxies are not moving. Rather, the distance between the galaxies are increasing. This is a purely general relativistic effect. And the way it comes about is that one can show that if matter on very large scale is distributed uniformly and isotropically, then one has the so-called Friedmann, Lemaitre, Robertson-Walker equations. From that, one has solutions in which one can prove that the distance between galaxies, they either increase with time or they shrink. So there are two solutions available. Depending upon the initial condition, one can choose which sector of the solution one is interested in. And since Hubble showed that the emission lines are redshifted, we are living in an expanding world. For a long time, cosmologists believed that the expanding universe, the rate of expansion is slowing down. But soon, with the observation by Perlmutter, Reis, and Schmidt, next slide, please.
Yes.
It was evident that we are living in a world that is actually not only expanding, but the rate of expansion is also increasing with time. And so as this slide gives a brief summary of the Friedmann, Lemaitre, Robertson-Walker model, and the redshift is really coming because of the fact that the universe is expanding. The scale of the expansion is described by this function A of t, and the redshift is nothing but the scale factor today divided by the scale factor at the time of the emission of the light minus 1. Next slide, please.
Yeah.
Yes, but am I audible?
Yes, yes.
Yeah. And the observational cosmologists, they would like to infer things about the universe by studying the emission from distant sources. So for example, if you have a source that is emitting with luminosity L, L stands for energy emitted per unit time, then at a distance d, if you are living in a Euclidean universe, the energy gets distributed over a spherical surface of 4 pi d square area. So therefore, the flux that one receives is given by L divided by 4 pi d square. But when one applies general relativity and goes to the curved nature of the so-called Friedmann, Lemaitre, Robertson-Walker geometry, this d is replaced by the so-called luminosity distance, which is given by the radial coordinate of the source times 1 plus redshift times the scale factor, the present scale of the universe. T0 represents the present age of the universe. Of course, optical astronomers, they prefer instead the apparent magnitude and the absolute magnitude relation. Apparent magnitude is nothing but minus 2.5, proportional to minus 2.5 log base 10 of the flux, while the absolute magnitude of a source is nothing but the apparent magnitude that the source would have if it was at a distance of 10 parsec. Parsec is nothing but 3.26 light years. And one can easily prove using this result that flux is equal to luminosity divided by 4 pi dl square, that the relation, if you have a source whose absolute magnitude is capital M and it is at a distance dl, luminosity distance dl, then its apparent magnitude satisfies such a relation. So in other words, the apparent magnitude minus the absolute magnitude of a source is 5 times log base 10 of luminosity distance divided by 10 parsecs. In other words, what this relation tells us is that if we have a source which is a standard candle means we can infer its absolute magnitude by independent means, and apparent magnitude anyway can be measured by optical telescope, then this being known from observation, this being inferred in an independent way, we can measure the luminosity distance, and the luminosity distance is clearly a function of the cosmological model one has. So in other words, if one has a standard candle, one can find out the entire cosmological details. Next slide, please.
Yeah.
Now, from general relativity itself, one can show that in principle, one can have a universe for which the scale factor not only increases with time, but the rate at which the scale factor is increasing also increases with time. That means there's some kind of a repulsive gravity. And general relativity allows it because in general relativity, pressure also causes gravitation. Just like in kinetic theory, after all, pressure is nothing but some kind of average kinetic energy density of the system, and kinetic energy would indeed cause gravitation. Similarly, in general relativity, any pressure can also cause effects in the space-time curvature. And in particular, if one has a strange kind of matter for which pressure is negative and pressure is less than minus 1/3 the energy density, such a exotic matter can cause universe to be accelerating. That means the scale factor not only increases with time, the rate of increase also increases with time. Incidentally, the cosmological constant, one of the so-called blunders of Einstein, but today has become a very important problem. It satisfies the equation of state that its pressure is exactly negative of its energy density. But today, to explain the observed accelerating universe, people do not want to invoke cosmological constant because cosmological constant has the fine-tuning problem associated with it. Next slide, please.
Yes.
Right. So just to summarize, that if you have a standard candle, one can chart out the detail of the cosmology. And it so turns out that a class of supernovae called type 1a supernovae, which are nothing but the explosion when matter falls onto a white dwarf, which has just attained the critical Chandrasekhar's critical mass. And such type 1 supernovae, type 1a supernovae, they behave like standard candles. And indeed, over many years, when Perlmutter, Rees, and Schmidt, they observed hundreds of type 1 supernovae, they from that, they got that luminosity distance, which showed that we live in a universe which is having late acceleration. That means today the second time derivative of the scale factor is positive. And for this discovery, Perlmutter, Reyes, and Schmidt were awarded the Nobel Prize. Incidentally, Professor Subir Sarkar, he has been analyzing the same set of data, and he has come to the conclusion that there is great deal of anisotropy, and maybe the main results could be due to the fact that our entire local group is actually moving towards a very massive super cluster. But again, the jury is still out on this subject. Next slide, please.
Yeah.
Right. So this is a summary of the fact that the observations suggest that the scale factor, instead of the rate going down with time, the rate is actually increasing. Now the question is, can we give an alternate explanation? Next slide, please.
Yes.
Next slide. This I have already explained.
Yes.
Yeah. Next slide, please. Right. So the idea is that the observation tells us that the accelerating universe is a late time phenomena. That means only for z less than 1, that means when the universe is almost 10 billion, today the universe age is about 14 billion years. But the late time acceleration corresponds to the fact that the scale factor, second time derivative of the scale factor being positive, is only when the universe was more than roughly 10 billion years old. So the question is, why did this so-called dark energy, the exotic matter for which pressure is less than minus 1/3 energy density, why did it start dominating only very recently? So there is also a fine-tuning effect associated with all dark energy models. And that is where I thought of the idea that how about if you have this sterile
I think there is a problem. Patrick?
Sir, his phone got disconnected.
Yeah. Now he's actually he's not only phone, I think both accounts. Yeah, both of them are actually got disconnected.
Yes, sir.
Just a minute.
Are you able to hear me now?
Yeah, now, great.
Yeah. So the idea was that.
However, we can't see you.
Okay.
Maybe that we can take care. Please go ahead. Please go ahead.
We can take care of it. Yes. Because the time is running out. I just want to quickly wind up. So the idea is that the late time acceleration, if you have sterile neutrinos which cause repulsive gravity, it could sort of in a natural way explain the so-called accelerating universe. The reason is that the stars and the supernovae, as soon as stars are formed, they lead to supernovae, and both stars and supernovae, they produce copious neutrinos. And if there are sterile neutrinos, the mixing of active neutrinos and sterile neutrinos would cause sterile neutrinos to be also produced. And since such things occur when the stars and supernovae start dominating, and that would happen late. And that could be then a natural explanation for why we have late time acceleration. Next slide, please.
Yes.
So the idea is very simple. So one imagines modifying the Einstein equation. The Einstein equation has the Ricci tensor minus half metric tensor Ricci scalar, and usually one has 8 pi g by c4, and T mu nu is the energy momentum tensor of normal matter. But supposing we postulate that the sterile neutrinos, the corresponding gravitational constant, instead of being positive g, it is minus g prime. Then this term can cause an accelerating universe. So when one applies the Einstein equation for the Friedmann-Lemaitre-Robertson-Walker model, one gets this extra piece which corresponds to repulsive gravity. So there are two FLRW equation, one for the first derivative of the scale factor, the other corresponding to the second derivative. So clearly, if there is a repulsive gravity due to sterile neutrino, this quantity being positive, if the this term dominates over the standard matter term, one can have accelerating universe. But one requires that this dominate the first term in the right hand side, and therefore if this dominates, then clearly the entire thing becomes negative, and therefore only Robertson-Walker model are viable if one invokes repulsive gravity from the sterile neutrino. Next slide, please.
Yeah.
And I will not go into the mathematical detail, just to say that we have used the data to constrain this parameter, this G prime, times the density parameter associated with the sterile neutrinos divided by the Newtonian gravitational constant G. And this N in this equation, if you have very light sterile neutrinos, so that sterile neutrino energy density goes as 1/4 power of the scale factor, while if you have N equal to 3, that corresponds to very heavy sterile neutrinos, so that the mass density goes as 1/a cube. We have taken both the cases, and we have constrained this parameter using the supernova cosmology project union catalog. Next slide, please. And this is where my student Priyambada Kameshwar and Varun Srivastava. Let's skip all these mathematical details concerning derivation of the luminosity distance. Let us straight go to the result. Yeah. So we have chosen the following parameters. For the density parameter associated with baryonic matter and we have chosen the canonical value 0.3, which comes from host of other astronomical observations. And we have chosen two different values of Hubble constant, one 65 kilometers per second per megaparsec, which is favored by the cosmic microwave radiation data, while the standard astronomers, optical astronomers, they find that the Hubble constant should be around 73 kilometers per second per megaparsec. So there's a tension between the CMB result and the traditional optical astronomy result. And we have therefore taken two different sets of Hubble constant, and we have used the weighted least square fit for the data. There are about 580 type 1a supernovae data for which the apparent magnitude minus the absolute magnitude data is available. So can we go to the next slide, please? Am I audible? Hello?
Yeah. Yes, yes.
Yeah. This is the data concerning massive sterile neutrinos. That means the energy density falling as 1/a cube. as the universe expands. So the upper panel is for the Hubble constant, 73 kilometers per second per megaparsec. And this gives us the alpha parameter to be 0.69, while the lower panel corresponds to the lower value of the Hubble constant. And here the alpha is somewhat smaller. And one can see that there is good fit up to high redshift type 1 supernovae for 65 kilometer per second megaparsec, while the higher Hubble constant, the last few points, they fall below the theoretical values. Next slide, please.
Yes.
Yeah, so this curves, they correspond to very light sterile neutrinos, for which the energy density fall off as 1/4 power of the scalar scale factor. And here again, we see that for two different values of the Hubble constant, 73 and 65, we have these fittings and weighted least square fittings. And we find that in this case, however, the high redshifts type 1a supernovae, they are not fitted so well. So in other words, the massive sterile neutrinos give us a better fit. But there's a caveat. Here we have assumed that the sterile neutrinos are sort of frozen. There are no extra sterile neutrinos being produced from the stars and the supernovae, and that is the whole idea that we wanted to use to begin with. And that is the work which we have to do now. So maybe with the injection of new sterile neutrinos, even we can fit the observed distance modulus with light sterile neutrinos. Can we go back 2 slides? Go back by 2 slides.
Results slide or previous to that?
Are you able to hear me?
Yeah, now we are at results slide. Result.
Yeah, this is the slide. Yeah. So what the fits tell us is that after all, the cosmological neutrino density is such that the density parameter for the neutrinos, cosmological neutrinos, is about 0.01. So the value that we have obtained for the alpha parameter, of course, the values are different.
Okay, looks like he has lost one of the connections. Yeah, please hang on. Can you hear my voice?
Yes, sir.
Okay. Let us, okay, now both his logins have disappeared. I'm sure he will get back. Just please bear with us. Yeah, one of them has come back. Yeah, Patrick, can you hear us?
Yes.
Yeah.
Are you able to hear me?
Yeah, now, yes, we are back.
Yeah. So, yes. So, from the weighted least square fits, we find that the G prime ought to be 10 times more than the Newtonian gravitational constant. So, what this is implying is that if sterile neutrinos cause anti-gravity, then the strength which they cause anti-gravity is roughly 10 times the usual Newtonian gravity. So does it tell something about it? I mean, are we here seeing a different gravitational scale? So the whole idea is that neutrinos, the mass of the neutrinos tell us that neutrinos are objects that we still don't understand much. And clearly, the mass of the neutrino tells us that there is new physics lurking behind neutrinos. And therefore, if indeed sterile neutrinos, which have been postulated, if they exist, there is no reason why sterile neutrinos should also cause usual gravity. And we are exploring the idea, what if sterile neutrinos cause anti-gravity? So I think I'll stop here. It would be more important to actually take questions.
Yes, that's right. There are quite a few of them actually waiting with their questions. Yes. So I'll stop your sharing so that
right.
They can hear better. Yeah, okay. So it's time now for the questions. I request any of you have questions, please raise your hand. And some of you have actually typed in your questions in the chat box, but you can still raise your hand and I'll come to you. Okay, let me then take up one question. I don't know if Snigdha, are you there on the call? Otherwise, I'll read that for you. Is Snigdha there on the call?
Yes, sir, I'm here.
Okay, can you please ask your question then?
Yes, sir.
Yeah, go ahead.
Sir, according to magnetostatics, the curl of magnetic field is constant, or the magnetic field has curl, but it is solenoid. It has no flux.
So what you mean is that the standard Maxwell's equation, the divergence of magnetic field is 0. And that is the reason why you don't see magnetic charge or magnetic monopoles.
Exactly, sir.
Yes. You're absolutely right. So far, no one has seen any magnetic monopole bearing magnetic charge. So therefore, all the observed magnetic field, they satisfy the equation divergence of magnetic field is 0.
That okay?
Yes, sir.
Okay. We go to Rita Mek. Can you please ask your question? Please go ahead.
Hello. Am I audible, sir?
Yes.
So my question is, in case of gravity, the quantization is called graviton. So what would be the quantization in case of repulsive gravity? This is my first question.
Yes.
And second question is dark energy somehow related with repulsive gravity or not?
Yes. So let me first take your second question. Yeah. So dark energy is the word representing all kinds of exotic matter whose pressure is negative. So they are characterized by a equation of state parameter W. So you write it as pressure equal to W times energy density, and Einstein's general relativity itself predicts that if your W is less than minus 1/3 energy density, that means less than minus 1/3, so that pressure is less than minus 1/3 energy density, Einstein's general relativity predicts that the corresponding gravity is repulsive. That follows from general relativity itself. So, in other words, whether in standard dark energy scenario, whether you have dark energy causing repulsive gravity, or in the scenario which I am talking about, where what we are doing is we are saying that the sterile neutrinos are such that if you have a ball of sterile neutrino having mass m, then this ball of sterile neutrinos produces a gravitational field, which is instead of minus g m divided by r square, it is plus g prime m divided by r square. So the gravitational field direction is different in the Newtonian way, but in the Einsteinian manner, you have the left-hand side r mu nu minus half g mu nu r is equal to 8 pi g by c4 t mu nu and minus 8 pi g prime by c4 t mu nu of the sterile neutrino. So therefore, whether you invoke dark energy to have repulsive gravity or a negative effective gravitational constant for sterile neutrinos to have repulsive gravity, the left-hand side of the Einstein equation is not changed, namely the r mu nu minus half g mu nu r, that is left untouched. And the quantization you're talking about, after all, how do you get this spin to quanta? What you do is you take the r mu nu minus half g mu nu r, which is a non-linear expression in terms of the metric tensor g mu nu and its derivatives up to second derivative of the metric tensor. What is done is one linearizes it by expanding the metric tensor g mu nu around the Minkowski tensor. So you take g mu nu, write it as g mu nu equal to eta mu nu plus h mu nu, where eta mu nu is the Minkowski tensor and h mu nu is a linear term which is much smaller than 1. And if you write down the Einstein equation using this approximation and only retain terms that are linear in h mu nu, you actually get a wave equation, namely D'Alembert operator acting on h mu nu equal to the source term. If there are no source, then D'Alembert operator acting on h mu nu is 0, which is a wave equation. And if you quantize it, you indeed get spin to quanta, which are termed as graviton. But remember, this mode of doing quantization is a perturbative way of doing quantum gravity. It doesn't take into account the non-linear aspect. And there are problems using quantization with the standard technique, except Ashtekar and his group, they have used the other way of quantizing general relativity, where they take the connection variable and the tetrad variable, and that's a separate. There are no gravitons. They're a separate way of quantization. So, have I answered your question?
Yes, sir. Yes, sir.
Are you able to hear me?
Yeah,
Yes.
I think,
Hello.
Yes,
Hello.
we can hear you very well.
I'm yes. Hello, sir. Hello.
Hello.
Yeah, we can hear you. So, can we move to the next question? Patrick, can you hear us?
Hello.
Yeah, can you hear us?
Are you able to hear me?
Yes, yes. Hello? Patrick, can you hear us? By the way, can anybody acknowledge that they can hear me?
I can hear you.
Okay.
I can hear you.
Okay. Patrick, can you hear us? Okay, so you'll have to hold on. Yeah, can you hear us, Patrick? Just a minute, there is a message.
Hello.
We can hear you.
Yeah. So
can you hear us, Patrick?
So does it answer both the question? The second was about dark energy, and the first was about whether in the repulsive gravity, whether graviton idea will change. The answer is no. The graviton idea comes from the linearizing the left-hand side of the Einstein equation, while repulsive gravity is to do with the right-hand side of the Einstein equation. Okay. Have I answered the question?
Yeah, but Patrick, can we check? Can you hear us?
Okay.
Can you hear us?
Yeah, more questions?
No, Patrick, can you hear us? Looks like he's not able to hear us. One second.
Are there more questions?
Patrick, can you hear us? Hello, Patrick, can you hear us?
Hello? Hello?
Patrick, can you hear us? I think we can hear you, but looks like you're not able to hear us.
Satya, can you maybe call him on phone?
Yes, actually, I hope I have his number. Oh my God, I don't have his phone number.
You can relog. You can send him a chat. Satya.
Yeah, I'm doing that. Several messages. Patrick, can you hear us? My God.
Hello?
Can you call Ratan on the phone?
Hello?
Patrick, we can hear you, but looks you are not able to hear.
Hello?
No, what's
Hello?
I don't have his number, unfortunately. Okay.
Hello?
Yeah.
Hello?
But he also doesn't seems to be seeing the messages.
Hello? Hello?
Hello, Patrick, can you hear us?
Yes, now I can hear.
Can you please quickly type your phone number on the chat box?
Yes, I'll do that.
I already made a blunder by not asking your phone number before. Yes, great. Now I'll call you if we lose you on audio, but now can you hear us?
Hello?
Can you hear us now?
Yes.
Okay, let us go to Swati Sachdeva for our question.
Hey, hi, good evening, Dr.
Hello?
Patrick and team.
Hello?
Hey, hi, do you hear me, sir?
Yes.
Okay, so thank you very much for giving us this platform, first of all. And I understood what you said. I have a question, and that is, I didn't understand what you mean by magnetic charge and the quantization of magnetic charge.
Sorry, there is a lot of echoing again.
Yeah.
Yeah.
Maybe Swati, if you can stop your mic. I can repeat
It's
for you
not
this
because
question.
of my mic.
Yeah, it's probably because of my system. One moment. Because I was trying out when I was not able to hear. Hello?
Yeah, we can hear you.
Sir, do you hear us?
Hello?
Patrick, can you hear us now?
Hello?
Yeah, Patrick, can you hear us now?
Sir, I think there is some issues with the internet.
Hello. Yes.
Yeah.
For some reason, if I the telephonic sound, I'm not able to hear you guys.
So what we can do, we can try. I mean, I don't know how well this will happen, but now I'll try to keep the the phone near this laptop, and I see if it can be communicated. Let us try one question. Okay.
Yes.
I think Swati, she was asking a question. Can you please repeat that?
Yes, hi, sir. I was asking, I didn't understand what's
Can
the
you hear
meaning of
the question?
magnetic charge. Yeah, I'm repeating my question. I didn't understand what Dr. Patrick said about magnetic charge, and also what does it mean by quantization of magnetic charge. Thank you.
All right. So the magnetic charge is nothing but the generalization of the electric charge. What is an electric charge? Electric charge is defined as that quantity that if you have two objects, one having electric charge Q1, the other having electric charge Q2, then the force between them is Q1, Q2 divided by square of the distance. Similarly, the question is that if I take a bar magnet which has a north pole and south pole, is it possible to have model the bar magnet instead of having a continuous way of dipoles being aligned? Can I think of a bar magnet as a magnetic north charge at one point, magnetic south charge at the other point, separated by a distance? Just like an electric dipole can be thought of as plus Q charge at one end and minus Q charge at the other end. So the idea of magnetic monopole was a theoretical idea of thinking of a magnetic dipole like a bar magnet as made of a magnetic north pole with charge plus G at one end and a magnetic south pole with charge minus G at the other end. And therefore, if you have such magnetic charges G1 and G2, then if you place two magnetic charges G1 and G2 with a distance d between them, then analogous to the electric field Coulombic force, you will have a magnetic force now, G1, G2 divided by square of the distance. And that's how the magnetic charge idea was sort of generated. It's a theoretical idea. Now,
Okay, sir, sorry for interrupting.
Sorry?
Sir, I have another question. Sorry for interrupting.
So
Sir, you said that.
Excuse me, Swati, can you please hold on for one more question, because I still have more than a dozen questions. I'll
Okay,
come back,
but
if you
just
time.
that is related to the topic we're discussing right now. I'm sorry.
Please go ahead then.
Yeah, thanks. Sir, as you said that we are just generally relating it with the electric charge, but the electric charges are the particle, like we talk about electrons. And how can I relate the particle thing with the magnetic charge? Because you said that north pole and the south pole. So are they particle also?
So the magnetic monopole are the corresponding hypothetical particles that carry the magnetic charge. So just like electrons carry electric charge, protons carry positive electric charge, quarks carry electric charge. Similarly, the particles that carry magnetic charge, they are called magnetic monopoles. But
Okay.
These are all theoretical ideas. No one has so far discovered any magnetic monopole.
Okay, thank you so much, sir.
Okay, thanks. So we go to Hemant. Hemant, there's a question. Hemant Adarkar.
Hi, Hemant.
Hemant, can you go ahead?
Hello.
Yeah, I'm just holding on. Hemant? Yeah.
Hi, Hemant. Good evening.
No, he's okay. We'll come back.
Come back later.
Yeah, Nitin Vashishta.
Yeah, Nitin Vashishta has been our student.
Yeah. Okay.
Yeah.
Please
It's
go ahead.
a nice talk. Yes, sir.
Yeah.
Can you hear me?
Speak a little louder because it is now going through a telephone.
Okay. Yeah. Can you hear me now?
Yeah.
Okay, yeah. So my question is, as far as fast radio burst FRB is concerned, so do we see the emission in other wavelength, windows as well? So because the multi-wavelength study of FRB will be helpful in the modeling of FRB.
Your voice is not very
Your voice is very low.
Can you increase the volume of your...
Yeah, can you hear me now?
Yeah, but yeah, go ahead, please.
Hello? Yeah, so my question is, hello? Hello? Yeah, so my question is does a... Hello?
Please go ahead.
Yeah, so my question is FRB, in the case of FRB, do we see the emission in other wavelength window as well? Because the multi-wavelength study of FRB will be helpful in the modeling of FRBs.
Can you speak loud and can you speak slow, please?
Yeah, if it's I can type the question so you can
okay,
read
fine.
it out.
Yeah.
Yes.
So, thanks.
Satya, can I ask the question till then?
Yeah. Please go ahead, Damon.
Yeah. Hi, Patrick. You as one of the researchers who failed to detect a monopole, I want to ask you this question because the monopoles that you consider are very massive.
Say that again.
Hello.
The monopoles that you consider are very...
The monopoles that you consider are rather massive.
Yeah, they are very astrophysically massive. Correct. You're right. That.
Yeah. So they seem to be closer to gut monopoles rather than Dirac's monopole.
Yeah. So the are having in
have
mind
you considered
object that have collected
monopole case?
Several heavy monopoles. It's not just one monopole, but population 3 stars which has absorbed many gut-sized monopoles, and then later on they have evolved and become black hole. So they are actually macroscopic objects which have absorbed many gut-scale monopoles.
Okay, fine. Thank you.
So the work, because our work is on gravitational waves, and therefore they need to be astrophysically massive.
Okay.
Am I audible?
Yeah, I can hear you.
Hello?
Satya,
Hello.
I could hear his answer.
Yes.
Hello.
Yeah, you can ask.
Hello.
Patrick, can you
Am I audible?
Can you hear us now?
Satya, you can go to the next question.
Yeah, but in between he has actually kept it in hold. So 1 minute.
He's asking.
I think there's something again. The voice says.
Can you hear us? Patrick, can you hear us?
The person you're calling is not answering. Please try later. आप जिस व्यक्ति
Hello.
Yeah, Patrick, can you hear us?
Hello.
Yeah, can you hear us now, Patrick?
Yes, now I can hear.
Okay. Actually, a question from Nitin. I think you already typed in the chat box.
Yeah, I have already asked this question.
Okay, so I request him to have a look at it. And now we'll move to, so 1 second.
So did Hemant
Yeah.
got my answer?
Yes. And he said fine and I can go. Now, Swagat Mishra.
Yeah, hi, Swagat.
Hi, Patrick. I have a couple of questions. The first one, both are related to your sterile neutrinos. The first one is
speak louder, please.
sure. The first question is about, so when you want to make a transition from your decelerating epoch to accelerating epoch, you actually require your, let's say for massive sterile neutrinos, you actually require your rho neutrinos to be higher than rho matter, right?
You require what? Rho neutrino to be higher than?
Rho matter.
No.
How do you get a double dot greater than 0 for massive neutrinos?
G prime, the
yeah.
G prime.
I see.
The
Yeah.
strength with which they cause anti-gravity, the G prime is greater. That's why our fitting shows that G prime has to be at least 10 times Newtonian gravitational constant.
Okay. The second question is, if you go to early,
has put your call on hold. Please stay on the line.
Again, there is a problem.
Hello.
Just hold on, Swagat, because again there is a problem from his end.
Yeah, it's all right.
Hello.
Yeah.
Yeah.
Hi, Patrick. Yeah.
You don't need density to be higher as long as G prime, the strength with which the sterile neutrinos cause anti-gravity, if G prime is at least 10 times the Newtonian gravitational constant, it can cause sufficient anti-gravity.
Yeah. But you are going to produce them in stars through some kind of interaction, right? Some kind of ultra weak interaction.
Sterile neutrinos are through the mixing. As you know, the active neutrinos and the sterile neutrinos, they are not in the mass eigenstates are not the same as the leptonic number eigenstate.
Yeah.
And the fact that the Z boson and the W boson, they have the width have been measured, means that the only way you can introduce a fourth neutrino is a neutrino that does not interact with WZ or for that matter any other weak interaction. The only way they can be generated is through the mixing. The fact that electron neutrino, ion neutrino, and tau lepton neutrino have masses means there are already 3 generations, nu1, nu2, nu3, and the sterile neutrino nu4. They mix with each other. They are individually eigenstates of the mass matrix, but electron neutrino being mixture of nu1, nu2, nu3. So therefore, it is a mixing which will generate sterile neutrinos from the active neutrino.
Yes, but they will also be produced in early universe.
They would be produced in what?
Early universe.
In the early universe.
Early universe, of course. Yes.
And could they not accelerate?
Density of sterile neutrinos, and also in the stars and supernovae which produce active neutrinos, the active neutrinos will oscillate into sterile neutrinos too.
Yeah.
Okay.
All right.
Okay. Let us go to, unfortunately, some of them could not hang on. There's a question from Vijay.
Hello.
Yeah, please.
Hello.
Good evening, sir.
Yeah, speak slightly louder.
Hello.
Yeah, we can hear you now. Yeah, please go ahead.
Sir, my first question is, out of the series of so many solutions like empty solution, non-empty solutions, which model is more consistent with our observation or Okay.
You speak loud but slowly. I mean.
Okay. Out of the series of so many solutions like empty solutions, non-empty solutions, which model is more consistent with our observations, or which model is the model in which we believe in much amount? I mean, and the second one is how we decide the value of cosmological constant.
Okay, so you're asking how cosmological constant problem
how
can
we
be solved. Sorry.
Repeat, Vijay, please repeat.
So how we decide the cosmological value of the cosmological constant? Actually, value of the cosmological constant.
How will you calculate, or how will you decide?
Yeah, how will we decide the value of cosmological constant?
Value of cosmological constant.
Yeah, so that is you're referring to the very well-known problem of the cosmological constant. See, theory-wise, from theoretical side, the cosmological constant value should be 10 raised to power 121 times the value of the cosmological constant that we estimate if you assume that the universe is accelerating due to a non-zero cosmological constant. This problem is called the cosmological constant problem. So the way the observers determine the value of the cosmological constant is that once you have a cosmological constant in the system, your Friedman, Lemaitre, Robertson, Walker equation, they get modified. For example, it becomes a dot square plus divided by a square plus ac square by a square is equal to 8 pi g by 3 times rho matter plus rho cosmological constant. And because you can estimate what is rho matter and you can estimate a dot square by a square today, because that is nothing but the square of the Hubble constant. From that, you can infer what is the mass density associated with the cosmological constant. And currently, the ratio of density of matter to mass density associated with cosmological constant is roughly about 3 divided by 7. This comes from the observation and certain assumption regarding the CMBR parameter estimation.
Okay.
Have I answered your question?
Yes, sir. And second question was, in which model we believe more? I mean, the empty, non-empty solutions, de Sitter models, and so on. So which model is more consistent with our observations?
Which model is more consistent with observation?
Yeah.
Between which models?
Hello?
Hello.
No. Which model is better? Which are the models one is talking about here?
Which of the models, Vijay, can you repeat?
Yeah, I mean, we saw series of the. I mean, so we saw so many models in masters. So which model is more consistent, or we believe more in that model?
What?
Well, there are many models, and the way model builders what they do is there are parameters in their theory, and the observation set, they take the same observation set. Different models will have different assumption and different parameters, and every model builder tries to fit the data by choosing certain parameters. So therefore, one cannot say which model is better. So at the moment, if you ask me which dark energy model is good, the answer is every model seems to be on equal footing, whether it is quintessence, whether it is cosmological constant, whether it is phantom model. You really cannot put your finger as to this model is better than the others. All models, they have parameters which are fine-tuned.
Okay. Patrick, there are a couple of questions. I hope we can quickly get them answered.
Sure.
Yeah, okay. So one is, again, Swagat Mishra, I think. Yeah. What I want to ask is that, does your analysis automatically take into account the fact that the sterile neutrinos produced in the early universe by flavor mixing would not cause an early dark energy? Do they stay in equilibrium like the rest of the neutrinos? In bracket, they would decouple earlier, of course. Plus, would they hang around as relics like the, this is SM neutrinos, standard model neutrinos?
So the question is about whether if sterile neutrinos are anti-gravitating, whether they can cause a accelerating universe earlier, that can happen only in the before the electroweak phase transition, when the neutrinos and the other matter they were thermally equilibrated. But once the decoupling took place, then the energy density associated with neutrinos fell below the baryonic energy density, and therefore once that happens, the anti-gravity associated with sterile neutrinos will be insignificant.
Okay.
So one would require, particularly if one is talking about massive sterile neutrinos, then one would require very high density of sterile neutrinos to give rise to accelerating universe in the early epoch. Does it answer my your question?
No, of course, this is a typed in question. I hope he got the answer. And I would like to go to YouTube, a couple of questions, if I can quickly ask you that.
Yes, sure.
This is from Shailesh Pincha. He said, what is the property of Dirac strings?
Yeah, that's a good question. So first of all, why this Dirac string? The reason is that if you have magnetic charge, that means if you have magnetic monopoles, then divergence of magnetic field is no longer zero. If divergence of magnetic field is no longer zero, magnetic field cannot be expressed as curl of vector potential, because you know anything that is curl of a vector field, its divergence necessarily has to be zero. So the fact that there are magnetic monopoles around, that is, you have assumed magnetic monopoles around, so you cannot write your magnetic field in terms of curl of a vector potential. But then Dirac showed that, well, you may not be able to write magnetic field as curl of a very well behaved vector potential, but you can always do the following. And this solution is given in many, many textbooks, that when there are magnetic monopoles, that means when divergence of V is not equal to zero, you can write down a vector potential which is differentiable and continuous everywhere except along a line. Along a line, the vector potential will be singular. And this line is called Dirac string because it's a single line. That's why it's called Dirac string. And the physical motivation is exactly like a solenoid. If you have a solenoid which is infinitely long and infinitely thin, then one end of the solenoid will be like magnetic charge, but the body of the solenoid is like the Dirac string, which where the vector potential is no longer continuous and differentiable, where the vector potential is singular. So in other words, the physical significance of the Dirac string is, let's say, mathematical line along which the vector potential is singular, because divergence of V, divergence of magnetic field not equal to zero, tells you that you cannot have everywhere smooth vector potential. Have I answered you?
Again, this is a question that was typed in the YouTube, Patrick. So I would like to take just one last question. It says, what is the motivation behind considering sterile neutrinos as anti-gravity candidates and not any other existing or unknown particles?
Yeah, so, okay. So first thing in physics is that you would not like to postulate newer and newer particles. It is called the Occam's razor principle. That is, whatever you have, with that, can you explain something? Because that is the whole idea of physics. Otherwise, if you try to explain every phenomena by using a different model, then you are not having a theory. So the whole 400 years of physics has shown that the phenomena that you observe all around us, they can be explained by a set of small number of laws. Now the question is, sterile neutrinos, the reason why sterile neutrinos were postulated was different. It was to explain the anomaly that was seen in the LSND experiment, namely excess antineutrinos in the decay of positive muons, and which was later on confirmed by mini boom data, where the pi plus decay showed excess anti-electron neutrinos and electron neutrinos. So a fourth neutrino was postulated. Well, we still don't know whether sterile neutrinos actually exist. But once sterile neutrino has been postulated, the idea is, can we give a theory which uses sterile neutrinos to explain accelerating universe? And that's the reason why I thought of using sterile neutrinos to... Hello?
Yes, Patrick, please go ahead. We can hear you.
Yeah, and that's the reason why one thinks of using sterile neutrino to explain the accelerating universe by demanding that the sterile neutrinos cause antigravity.
Okay, so I think, Patrick, we have taken up all the questions on both platforms. So once again, I want to thank you for taking up all these questions. And also, of course, we have been kind of troubled a little bit by the technology here, but in spite of that, you stayed on, and also the participants stayed on. Of course, maybe a few of them could not hold on for a while, but I'm sure they got most of the answers that they have been asking. It is already now close to 8 o'clock. So I would like to thank you on behalf of all the participants for taking time.
I enjoyed it.
Thank you. Thank you so much. And thanks everyone. Thanks all the participants who have patiently bore with us for the technology challenges in between. Some interruptions happened. Thank you very much. And we all look forward to having you again with us on Monday at 6 p.m. Okay, with for Professor Lalit Pant's talk. Thank you very much, and good night, and take care.
Thank you, everyone. Goodbye.
Bye. Thank you. Thank you, Patrick.